Hello, I'm the mystified Mr. Daycock, and today I'm going to be teaching you about solving second-order differential equations where the auxiliary equation has complex roots. Okay, so let's get going. We're going to start in pretty much exactly the same way as we have done before. We're going to write down the auxiliary equation, which in this case is alpha squared minus 4 alpha plus 13 equal to 0. And then we're going to solve that. Unsurprisingly, this doesn't factorize as we're talking about situations where we have complex roots. So we're going to go to our quadratic formula, which gives us alpha is going to be equal to minus b, so minus negative 4, plus or minus the square root of b squared, which is negative 4 squared, minus 4 times a times c, so times 1 times 13. All over 2. And let's start doing some simplification. That means gives us alpha is equal to 4 plus or minus the square root of 16 minus 4 times 13 is 52 all over 2. Which gives us alpha is equal to 4 divided by 2 is 2 plus or minus this divided by, we're going to get half of it, isn't it? If we divide by 2 it's the same as half of it. And we get the square root of 16 minus 52. Well, that's going to give us negative 36. And so this is equal to 2 plus or minus a half of the square root of negative 36 is 6i. And so we get is equal to 2 plus or minus 3i. Now, key thing to notice. We have two solutions here, 2 plus 3i and 2 minus 3i. As you should know from complex numbers, if all the coefficients are real, which they will be in the vast majority of cases you're dealing with, if all the coefficients are real, then we will absolutely get a pair of complex solutions, a complex conjugate pair, where the only difference is the plus and minus, which is really, really useful and then makes it much, much easier to deal with. So we can think of this as, in general, we'll have our solutions being alpha equal to a plus bi. A plus or minus bi. We get one, and we still have two situations here, two things, but the two things are basically this and this, rather than this and this. So you want to think of it in terms of the coefficients of the real and imaginary part. And I'll show you why in a minute. So we have our two solutions. We've got alpha is equal to 2 plus 3i, and we've got alpha equals 2 minus 3i. At this point, we just apply exactly the same formula. Well, we won't be doing in the future, but for now, to show you why we get to this actually quite distinct form, I'm going to go through and just plug it in as usual. And so we get our general solution being y equals a multiplied by e to the 2 plus 3i x plus b lots of e to the 2 minus 3i x. And we need to put that in brackets because that's our coefficient of the x. We're multiplying the whole thing by x. And now you can actually just leave it at this. This is actually correct. This is a valid answer. But it's really, really awkward, and you'll find that often like this, a and b might actually be imaginary numbers, despite the equation originally being entirely real. And we kind of want to get all the imaginary numbers out of there. So what I'm going to do is I'm going to expand these brackets up here. And I'm going to get y is equal to a e to the 2x plus 3ix plus b e to the 2x minus 3ix. And then I'm going to apply my laws of indices. So I get y is equal to a e to the 2x e to the 3ix plus b lots of e to the 2x times e to the minus 3ix. And now we should notice we have a nice common factor here, this e to the 2x. So we're going to factor that out, and we get y is equal to e to the 2x multiplied by a e to the 3ix plus b e to the minus 3ix. but this should be familiar. This here is just a complex number in exponential form, and it's a complex number with magnitude 1, size of 1, modulus of 1. And as such, we can write it in sine cosine form, in argument form, as it were. And so I'm going to write down these two complex numbers in argument form. So we get y is equal to e to the 2x multiplied by a lots of cosine of 3x. Because remember, we're dealing with a situation of e to the I theta here, where theta is 3x. So cosine of 3x plus I sine of 3x and then we get plus b cosine of negative 3x, but cosine of negatives, because of the type of function cosine is, because it's an even function, we end up with that just being 3x, and then plus I sine of negative 3x, but again, because sine is an odd function, we can actually write that as minus I sine of 3x. And this is really helpful. Let's zoom out a little bit. This is really helpful because we actually have this cosine 3x twice, and we have this sine 3x twice, and we don't have that negative anymore. We've no longer got 3 and minus 3, we've got just 3 and 3 in both cases, which is helpful. And now I'm going to expand those brackets, so I get y is equal to e to the 2x lots of a cosine 3x plus ai sine of 3x plus b cosine 3x minus b sine I sine of 3x. And now I'm going to gather like terms in terms of cosine and sine, and so I'm going to end up with y is equal to e to the 2x lots of a plus b lots of cosine of 3x plus, oh wait, let's be careful here. No, that's right, that's entirely right, sorry. Plus ai plus minus, let's be careful, minus bi of sine of 3x. Okay. And now at this point you might be going, wait a minute, how is that easier? How have we made anything easier at all? It seems like far more complicated. But actually, now at this point, I'm just going to take this and redefine them. A and B were arbitrary constants. Therefore, AI and BI are also just constants. So what I am going to do is I am going to say, what if I'm calling it A plus B? I'm going to call it A1. And I'm going to say AI plus BI, I'm going to call it B1. And now I can write this as y is equal to e to the 2x lots of a1 cosine of 3x plus b1 cosine of 3x. And now this is a much simpler form because there is one key thing: there are no complex numbers in there at all. This can be all real. We have x is entirely real everywhere, and these constants are arbitrary constants, and so they can be entirely real as well. So everything here is real. So although it is valid to write it as y is equal to a e to the 2 plus 3i x plus b lots of e to the 2 minus 3i x. Although that's valid, it's got complex parts to it, and we want a real solution to this differential equation. And ultimately, interestingly, if you did pick this, every time you calculated it, if for every real x you put in, you would get a real y out, but it's not very nice. Although it would work, it's really, you'd have to go through complex numbers to get a real answer out. And this here avoids that. So this form is our general solution form that we're looking for, and it avoids that problem of putting a real number in and having to go through some complex numbers until we get a real number out again. Instead, we can just go real, 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 and real. So this form is the form you want to look for if you have complex solutions. So this leaves us with our last one. If your solutions, if alpha is equal to a plus bi, let's be clear, plus or minus bi, then your solutions will be of the form y equals, let's be careful, general solution, y equals e to the ax. And notice the real part is still in exactly the same form we would normally expect, multiplied by a cosine of bx plus b sine of bx. And that there is your general form if you have complex conjugate roots to the auxiliary equation. Okay, so now we know that, now we have that form. Let's just apply it to another question. If I can find it. Oh, that's a fair bit of work. Right, here we are. Find the general solution of this equation. So, as always, write down the auxiliary equation, which is alpha plus 6 alpha, alpha squared plus 6 alpha plus 10 equals 0. You check the discriminant at this point, or what have you, to check whether or not it is two distinct roots, repeated roots, or complex roots. It's complex roots, and you will get minus 6 plus or minus square root of 36 minus 10 times 4 is 40 all over 2, which gives us minus 6 plus or minus the square root of 4 over 2, minus 4 over 2, which is minus 3 plus or minus I. And then we can just apply this form with our a equals negative 3 and our b is equal to 1 because we've got 1i. And so our general solution is y equals e to the power of negative 3x multiplied by a lot of cosine of 1x, so in fact in this case just x, plus b lots of sine of 1x, so again just x. There's a 1 there from the b. And there you go. Very quickly solved that equation using this form. And once you know the form, and once you've learnt the form, and you know it off by heart, solving these homogeneous second order differential equations is very simple. Now, I threw the word homogeneous in there at the end. What does that mean? Well, that's what we're talking about next time when we look at non-homogeneous ones. Okay, thank you very much for watching, and I'll see you in the next video.